Alright, welcome back. So, basically today we are going to be going over molecule polarity and dipole theory. So we're basically going to be looking at polar molecules and polar bonds. So we will need to know what all that means first. So first of all, we have, what is a polar molecule? This is a molecule that's going to have a negative charge, or a negative electron charge specifically, that's not distributed evenly between the atoms that make up the entire molecule. So if the electrons aren't dispersed evenly throughout, we're going to get a partially positive end. So this is the symbol we do for partially positive. So I know that weird little symbol right here. So this is the Greek lowercase delta. So how you make that is you kind of like draw an S and then finish it 3/4 way. So it's almost like you create an 8, but not fully. So that's just the symbol there for delta. So that just means it's partially positive, and we also have a partially negative charge on both sides of a molecule. So of course a nonpolar molecule is going to be a molecule with an even electron distribution between the atoms that make up the entire molecule. So first of all, it's like we need to make sure that we understand the difference between a molecule and the bond, because we're going to talk about both, so molecule polarity and bond polarity. So little reminder, electronegativity is the ability of an atom to attract electrons to itself. Now, we've already looked at these numbers, so if you remember, go into your data booklet, and we've seen the electronegativity values here, right? So metals, we have low electronegativities, and of course our nonmetals, we have generally high electronegativities. So we've already seen these numbers here. But what we're going to do is actually take the difference, and of course you know that just means subtract the two, and this will determine the bond polarity, right, just between two atoms. So we're going to have to look at the bond polarity before we actually figure out the entire molecule. So for a bond polarity, based on what we can have the polarity of a covalent bond is going to be the difference in electronegativities. That's it. So the different types that we can get a nonpolar covalent bond. So this is where the electrons are shared evenly between the bonded atoms, and what we're going to be looking for is the difference between 0 and 0.3. Now, if you actually Google, so if you actually Google like bond polarity, you might see some places to say 0.4. Now 0.4 is kind of the gray area between that polar and a nonpolar. I generally go with 0.3, just because then when we get molecules like methane and CH4, that's nonpolar, and there's a difference between 0.4 there, but then you get H2S. That's technically slightly polar molecule, which has, or they consider that bond a little slightly polar, so and it's 0.4 difference. So anyway, just for that sake, instead of that confusing, I just go between 0 and 0.3 for nonpolar. So then when we go polar, we're going to have 0.4 to 1.6. So, and this is where the electrons are shared unevenly between the bonded atoms, right? So when we take the electronegativity difference between two things being bonded, we should see a number between 0.4 and 1.6. Now, if we get electrons being transferred from one atom to another, we are going to see a number when we take the difference of 1.7 and above. Alright, so those are the numbers we're looking for. So polar covalent bonds form when two different atoms share electrons, and those electron pairs are not shared evenly. So this is for polar covalent bonds, right? Because we have that unequal sharing of the electrons are more attracted to the molecule with the higher electronegativity, and this is what creates that dipole. So the side of the bond where the electrons spend more time is the partially negative, because remember, electrons are negatively charged, and the other side, because the electrons are shifting over, that will be the partially positive. So for the instance of HCl, we'll notice right here, and we see right here specifically, so because chlorine has a higher electronegativity, right, if we go look at chlorine has electronegativity of 3.2, hydrogen, 2.2. So chlorine has a higher electronegativity. So basically our two different diagrams right here are two different ways that we can represent the molecule being polar. So notice right here on how we have this arrow, but it looks like a little plus sign right here. So what this arrow is showing in the first diagram of where the electrons are moving. So these green blobs you see right here are called the electron clouds. So because it's around chlorine, the electrons are spending more time over here. So that's why the arrow is pointing to where the molecules are going. Now we can also kind of do the same notation that we have right here, is label this side partially negative and this side partially positive. This is the way that we're probably going to be doing it right here, is that we're mostly going to be just highlighting the molecule right here. We have that bond and highlighting which one is going to be the partial positive and the partial negative. Now, as I mentioned a little bit earlier, is that with the bonding, we kind of want to have the hard numbers, but not really, because technically, like, this is kind of a bonding continuum. Like, there's a lot of gray area around these numbers right here, but generally where I try to keep it, so, just for the sake of trying to keep everything consistent, between that 0 and 0.3, this is going to be our non-polar covalent bonds. Here, between 0.4 and 1.6, this is where we're going to get our polar covalent bonds. And 1.7 and above, this is where we're going to get our ionic bonding. So these numbers, yes, this is what we're going to be using, and this is how we're going to describe it. All right. So even though I know if you do Google, they're going to say 0.4 is the cutoff point, blah blah. We want to kind of have some numbers right here and just try to take the ambiguity out of it. So these are the numbers that I'm just deciding to kind of go with. So just so you know. All right. Now, once again, I have the bonding continuum right here. So basically what we're going to do is like we're talking about taking the difference between them. So let's say we had our oxygen, right? So what we're going to do is first look at, well, what's the electronegativity of oxygen, right, for the O2. So we go to our periodic table. We find oxygen is 3.4. All right, cool. So we're going to go back. Now, when we take the electronegativity difference, so we have one oxygen right here, 3.4. This oxygen is also 3. Oh, that's a weird look for 3.4. So there's the electronegativity. So when we take the difference, now we always want to get a positive number, so always go the big number minus the small one. So we just go En is equal to, we take 3.4 minus 3.4, and then we get a number of 0. So this bonding type is, of course, non-polar covalent, which we can shorthand NPC if we want to. The next one, we're going to take the nitrogen and the hydrogen, right? So go to our data booklet. Our nitrogen is right here, so 3.0. Hydrogen, I already have highlight right here, 2.6. So we're going to take two of those. So our nitrogen, 3.0. Hydrogen, 2.2. Did I say 2.6 earlier? I meant 2.2. So when we go the electronegativity difference, I always take the bigger number, 3.0, minus the smaller number, 2.2, and we're left with 0.8. So this number right here, looking at our chart, so this falls in between our 4 and our 1.6. So we call this a polar covalent bond. And I forgot to put the word bond here as well. Which, I guess NPC goes to NPCB. Non-polar covalent bond. And now our last one, our potassium fluoride. So same thing. We find potassium, which is right here, 0.8. Then, of course, we find fluorine, over here at 4.0. So we have a look at that again. So our potassium, once again, that one was 0.8. We reference it. Our fluorine was 4.0. So take the electronegativity difference. We go 4.0 minus 0.8, and we're left with 3.2. And this, of course, would make an ionic bond. Right, so that just describes the relative ability. Now, of course, we know right here, especially for nitrogen, it can take more bonds and everything like that. So if once we start looking at molecules, we're going to have to do these calculations a lot. But this just kind of describes the relative idea of, like, how things are bonding, right? Just the degree of how the electrons are being shared. Now, that is bond polarity. Our next little step, we're going to tie this into molecular polarity or molecule polarity. So just because we have a polar bond, it does not necessarily mean that we're going to get a polar molecule. So there's more to it than that, right? So, of course, the electronegativity values And of course, the bond polarity values matter. But what also matters, of course, is what we learned not too long ago, our VSEPR theory. So how the molecules actually look in three-dimensional space will matter massively when we look at how a molecule can be polar or nonpolar, right? Now, once again, this calculation up here, this is just for the bond, right? So it's just two atoms bonded together. Now, for molecules, we need to look at all the bonds. So bond dipole, which just went over, right? It's a bond with one end having a slightly negative and the other having a slightly positive because of the unequal sharing of the electrons, right? So sometimes a bond dipole can be represented with that funky looking arrow that we looked at as well, which points from the lower to the higher electronegativities, right? Or we can use these partial signs. It doesn't really matter. Now, a molecular dipole or a molecule dipole is going to be the sum of all the bond dipoles. Now, we're not going to add all of them together. There's going to be some rules because trying to add up bond dipoles in three-dimensional space might be a little bit challenging, especially for our tetrahedrals and our pyramidals, so we're not going to do that. But anyway, you kind of need to know what it is. So a molecular dipole is technically the sum of all the bond dipoles. So one end of the molecule has more electron character than the other. So and all this will determine whether a molecule is going to be polar or non-polar. So now we're going to get into, well, how does that look? Well, vector quantities and bond dipoles. Now, we're not going to get, if you've done physics, this might be bringing in some bad memories, but we're not going to be looking at, all of the stuff, right? So vector quantities, bond dipoles. So if you remember vectors, learned this from Science 10, they have size and direction, so direction matters. So I'm just going to go over the process of how all this ties in together. All right, so if dipoles are equal but in opposite direction, they're going to cancel. I probably spelled that wrong. Probably still spelled wrong, but whatever. Now, and of course, if the bond dipoles don't balance, or if they point in the same direction, they're going to add together. Now, we're just going to look at two examples right here. So I specifically want to choose not the exact same molecule, but, ones that are very similar. So I'm just going to get a completely clean sheet here. So by doing this, and by doing this. This is kind of show you, all right, so our carbon dioxide and our HCN. So when we look at carbon dioxide, this is linear. And of course, HCN is also linear. So this is a good one where we can actually see these vectors and stuff like that canceling it. So I'm just going to write the electronegativities just kind of below the atom. So for carbon, the electronegativity is 2.6, oxygen is 3.4, and this one is 3.4. Carbon is 2.6, nitrogen is 3.0, hydrogen is 2.2. Now, when we look at the oxygen and carbon bond, the electronegativity difference this should be 0.8, if my math is correct. So, I'm just going to put this in a different color. So what this means is that the vector, if we want to look at vectors, so one is pulling, so in this bond right here between this carbon and this oxygen is pulling with a strength of 0.8. But we also have the other one pulling with the exact same magnitude in the other direction. Now, if you remember physics from grade 10 science, we have vectors that are equal in magnitude, but they're in opposite directions. So the net is just going to be a big fat 0, because one of these right here, if we say right is the positive direction and left is negative direction, we go 0.8 plus a negative 0.8 and it gives us 0. So we have a net pull of basically 0, right? I know there's no units to this, but so, and that's why where they cancel out, this linear molecule right here, CO2, is going to be non-polar for that reason. Now we're going to notice something different happening with our HCN. So when we look at the bonds right here, we have hydrogen and carbon, and then we have carbon and nitrogen. So when we get the electronegativity difference of hydrogen and carbon, we go 2.6 minus 2.2, and we have 0.4. So this is slightly polar covalent. Now for our carbon and nitrogen, we go 3.0 minus 2.6, and we also have 0.4. So we'll notice right here they have the exact same strength, right? The exact same magnitude. But when we look at the direction, when we look at the carbon and hydrogen, carbon is the more electronegative atom, so the electrons are going to be going this way. Now when we look at the carbon and nitrogen bond, well, nitrogen's more electronegative atom, so we get 0.4 going that way. So we'll notice our net right here and the way I have it drawn. So we have a net force of 0.8, once again, whatever those units are, and of course going to the right. So, in that case, what we can do is just take this, and we can just have one big arrow extending over the entire molecule, like this. And then we can call this one polar for that reason. Whereas technically for that carbon dioxide, because they cancel out, we're not going to do this. It can just stay exactly like that. So there's no net pull, so we don't put anything in. And this right here, we get partially negative, and over here, partially positive. So that's kind of why the directions matter. Now, I know that was a lot to kind of take in there, which is fine, but that's why the directions kind of matter. So when we look at stuff right here, so the dipoles are equal and opposite, they cancel. So the CO2 is nonpolar, and if the dipoles add together or they're not balanced, they kind of add together, and that's our HCN, right? So the whole point of that is just show you that the shape of the molecule and, of course, the peripheral atoms are going to be important in determining if the molecule is polar. Now, we have to remember all perfectly symmetrical molecules are going to be non-polar. Now, what does perfectly symmetrical mean? So these are any atoms that have no lone pairs around the central atom. Now, let's go back to this example right here. So CO2 and HCN. Now, I know there's a lot of writing right here. So carbon has 0 lone pairs on the central atom, right? Now, we do know oxygen has some lone pairs. But perfectly symmetrical, when we look at it, has no lone pairs. We have 180 degrees between every single atom. And notice how we have the exact same element on both sides, both oxygen, right? So this is another reason why CO2 is going to be nonpolar, is that it has this perfect symmetry going on, right? And as we've seen, right, if it's perfectly symmetrical, the vectors are pulling with the same magnitude but in opposite direction, so they're going to cancel. All perfectly symmetrical molecules with no lone pairs will have this. Whereas if we have a non-symmetrical molecule like HCN, right, once again, no lone pairs, the bond angles are the same around, but when we look at the left and the right, we have two different atoms. Non-symmetrical, polar molecule. That's going to be a very common theme that we're going to see in this particular set. And the reason why we have, you know, the ones with no lone pairs is that lone pairs repel all the other atoms. So molecules that generally have lone pairs are going to be polar. Now, and that's why I say generally, there's going to be a few rules that we're going to have to follow. So, first steps to figure out the polarity of a molecule. So step number 1 is we're going to draw the Lewis or structural diagrams for the molecule, right? So just know what we're doing. Then we're going to use our VSEPR theory to predict the molecule shape. Next, we're going to use electronegativity to determine the polarity of each bond, and we're going to label. Now, technically, this is what we're doing, adding bond dipoles to determine the overall molecule's polar or nonpolar. This is the cheat sheet right here, or we're going to use the below chart. Now, this is a lot. Once again, there's going to be lots of practice for this. but we're going to see some trends. So, in order to have, first of all, a polar molecule, this is going to be key, all right? We have a little asterisk right here, so sorry, we should write this down here. So polar molecules need to have at least one polar covalent bond. All right, so that is just one thing that we're just going to have to get used to seeing. And that's why we're going up here is like even on the previous page, once again, I'm going back right here, how I found the electronegativity differences first, right? After I drew everything out, I found the electronegativity difference. Remember, I said these molecules are polar or nonpolar in the last step, right? But the first step was figure out, well, what's the electronegativity differences? Now, what we're kind of looking for here is we're looking for at least one polar covalent bond. So as long as we have one bond that's unequally sharing the electrons, then the entire molecule will have a chance to, once again, on-share the electrons or have an unequal sharing of the electrons. It'd help if I spoke proper English every once in a while. Now, if we have a molecule that has all non-polar covalent bonds, well, if we don't have an unequal sharing of the electrons in a bond, it's impossible to have it in the molecule. So this is always step number one in finding a polar molecule, is checking the electronegativity differences, right? So once we have that, then we're going to be looking at the shape. So if we have a polar covalent bond and we have a diatomic with two different atoms attached, we're going to have a polar bond, right? That's always the case. And it should make sense for a diatomic with only two atoms. Now for our VSEPR shapes, right? So if we have one polar covalent bond and we have nitrogen, arsenic, or phosphorus as a central atom, we are always going to have a polar molecule. Same thing with our V-shaped, right? As long as we have one polar covalent bond and we have a V-shape, we are going to have a polar molecule. All right? So these are the ones right here that I figure are the nice ones. Now, tetrahedral, linear, and trigonal planar. We will notice that three of these shapes are together, all right? And the reason for that is because carbon can form all three of these shapes. And carbon does not have a lone pair. So once again, when we go back to this symmetrical thing, right? No lone pairs. If it has no lone pairs, it's going to be symmetrical. So that's why carbon's in here. Now, when we look at the things for carbon, so these shapes, we need to have at least that one polar covalent bond, but two different peripheral atoms. At least two different peripheral atoms are attached. And same thing with boron. Two different peripheral atoms. So look at all these examples right here. So carbon is a central atom, hydrogen, chlorine. Two different peripheral atoms, polar. Carbon is a central atom, even though there's two of them are central atoms, that's fine. Hydrogen and fluorine are peripheral atoms. It's going to be non-polar. It's going to be polar. Okay? So these are the rules for the polar molecules. We need to look for that one polar covalent bond, and then we have this shape structure. Now the non-polar ones are a little easier to determine. That's what we have right here. So here's that thing. Must have one, at least one polar covalent bond. So if we do the electronegativity difference and we do find that they're all non-polar covalent bonds in the molecule, well, the molecule is non-polar. So like for a polar molecule, it's kind of, your checklist is like, does it have a polar bond? Yes or no? If no, non-polar. If yes, look at the shape. Right? So for our non-polar ones, all elements are going to be non-polar. It doesn't matter what they are. Now we'll notice V-shaped and pyramidal do not show up here. They have lone pairs, so those shapes are generally polar. They just need a polar covalent bond. But for the tetrahedral, linear, and trigonal planar, this is how we can tell if we have one of these shapes and whether they're polar or non-polar. So carbon or silicon is a central atom, and only one type of peripheral atom, that's it. And look at all of our examples, same thing with the boron. CH4, CCl4, Si2H6, C5H12. So notice how we have central atom, carbon, only hydrogen attached. Non-polar. Right? Carbon is the central atom right here, only chlorine attached, non-polar. Silicon is the central atom, right? And there's two of them. There's two central atoms, that's fine, but both are silicon. It's the exact same element, right? Boom, only hydrogen as the peripheral, right? And even this one right here, so C5H12. Yes, there's 5 carbons. Oops, sorry. Yes, there's 5 carbons. They are all central atoms, right? This is the only peripheral, the hydrogen. So that will be non-polar. So, now that was a lot. That's why you're going to get to the practice right here. So I'm going to skip over the HBr because that's a diatomic. That one isn't as fun. I'm going to do the PCl3 with you guys. So for PCl3, we'll start off right here. So we need a Lewis formula. So phosphorus, central. It'll look like this. And then our chlorine is set up. Like this. And then of course the last one look like that. Now phosphorus we can tell is our central atom, and chlorines are the peripheral. So our stereochemical formula, phosphorus has one lone pair and we have 3 bonding pairs. So we are going to get our phosphorus in the middle. We're going to get chlorine on the bottom of the paper. We are going to get chlorine coming out of the paper. And we're going to get chlorine going behind. So this is, of course, pyramidal. Sorry, I can write that a little neater for you. Alright, so all these steps right here, this should be nothing new. The bond polarity and the molecule polarity are the 2 new steps, alright? So, once again, in order for a molecule to be polar, we need to have at least one polar covalent bond, so that's why we have this step right here. Next, molecule polarity, basically we're looking at shape, alright? Actually, the shape and then bond polarity right here, and that'll determine everything. So right away, okay, pyramidal. When I look at the possibilities, we'll notice how pyramidal is not up here in that nonpolar range, right? Because pyramidal is over here. Pyramidal is always going to be a polar shape. Now, once again, that's the shape, right? We need to do this step right here. Is there at least one polar covalent bond? If the answer is yes, then the molecule is going to be polar because the shape and the polar covalent bond match. If our answer is no here, and it's all nonpolar covalent bonds, then PCl3 is going to be nonpolar. So, let's have a look. So we have, the only type of bond we have is phosphorus bonded with chlorine. So we go to our data booklet, we find phosphorus is 2.2, chlorine is 3.2. So we go 3.2 minus 2.2, and we're left with 1.0. So this is a polar covalent bond. Now, as mentioned before, pyramidal, that shape, yes, is polar. We have our polar covalent bond, so we have a yes for shape and a yes for bond polarity. So the molecule will be polar. And that's how we go through this. Alright? So there's a few more right here. We have HBr, H2O, MBr3. If you turn over the next page, you got SiO2 and CS2. And this will be the cutoff for quiz number 3 for you guys. So after you complete these right here, once again, you can hop onto Google Classroom, check the notes to kind of make sure if you got all those. Or what you can do as well is open up your workbooks, and I'm pretty sure there is a page dedicated to all this as well. Alright? So now it's time to kind of put some work in, go through all these right here, and in the next lesson we will learn what these polar things mean for the molecules. So we're going to be looking at kind of their physical properties. So anyway, that's it, and see you guys later.